afternoon, friends. We shall continue our discussions on two-port network. In the last class, we have established relations between the voltages and currents in terms of Y parameters and Z parameters. Let us take a simple example. Of a resistive network. Say these are the values given: 5 ohms, 10 ohms, 10 ohms, 20 ohms and 20 ohms. It is just an arbitrary set of values I have taken. What would be the Z parameters? Say Z11. It is the voltage at this point, at this port, divided by the current when this is kept open. So Z11 is 5 ohms plus 10 ohms in parallel with 10 plus 20, 30. So it will be 10 into 30 by 10 plus 30. So that gives me 300 by 40, 7.5 plus 5. So it gives me 12.5 ohms. Okay. Similarly, what will be Z22? It is the impedance in from this side when this is kept open. So it is 20 plus 20 in parallel with 20. 10. So that is 10, 30 ohms. I should write this ohms. This is also in ohms. Okay. Z12, if you want to determine, it will be V1 by I2 when I1 is 0. So if I keep it open, send a current here, how much is the voltage drop here? That means how much is the voltage here? Since this is kept open, this voltage is kept open, and I am forcing in a voltage from this end. So it is V2 by I1, and how much is that? Now in our earlier discussion, for a ladder network, it is something like a ladder structure. So if I have a unit current here, okay, V2 by I1, Z12 is V1 by I2. So I am sending in a current here. Say you can take 1 ampere here. Say if 1 ampere flows through this, then that will give me how much? 20 volts drop here. 20 by 20, 1 ampere here. So 1 plus 1, 2 amperes, and that will make it. It is V2 by I1 you can take, or somebody may take V1 by I2. In the morning we discussed Z12 is same as Z21. So either way, if I calculate V2 by I1, that is the voltage obtained here when I am sending a current here. Okay. So if 1 ampere current flows through this, 20 plus 10, 30 volts. 30 volts by 10 ohm, so 3 ampere. So 3 ampere plus 1 ampere, 4 amperes is the current here. Okay. So for a unit current here, 1 ampere current here, 4 ampere of current will flow through this. So, and how much will be the corresponding voltage here? Voltage is 20 volts. So 20 volts by 4 ampere, that is 5 ohms. Okay. So Z12 is 5 ohms, is same as Z21. Is that all right? One may go for star delta reduction and get the T formation, and then we will get the same values. For passive network, since we can always find an equivalent T or a pi for any network, Now, if I have a voltage V1 say 10 volts and short this and record the current through this, how much is the current through this? Suppose this is ZA, this is ZB, this is ZC. Okay. When I am shorting this and measuring the ratio of voltage to current, how much is the voltage V1 by I2 when this is shorted? When this is shorted, ZA plus combination of ZB, ZC is the overall impedance. So, overall impedance is ZA plus ZB, ZC by ZB plus ZC. Okay. And how much is the current flowing through this? Voltage by Z overall, this is this current, and a fraction of that is flowing through this. What fraction is it? It is the other impedance ZC by ZB plus ZC. Is that all right? And how much does it come out to be? V by Z overall is this. So, I can write ZAZB, ZAZC plus ZBZC. So, I will write in this form sigma ZAZB, which means all such terms taken together by ZB plus ZC. Okay. So, V by sigma ZAZB by ZB plus ZC into ZC by ZB plus ZC. So, ZB plus ZC gets cancelled. Okay. So, that gives me V by, this is this. Okay. So, V1 by I2 is V1 by sigma ZB ZA ZB and multiplied by ZC. Is that all right? ZC is this, and these are all combination terms. If I apply a voltage here and short circuit this, measure the current, what will be this voltage by this current? This voltage by this current? It will be same ZC divided by the same term, is it not? From symmetry. So, is also equal to V2 by I1. Okay. V1 by I2 when V2 shorted and V2 by I1 when V1 shorted. Okay. That means in any multi-port network, if I inject a voltage at one terminal pair and if I short circuit any other port pairs, alright, any other port and measure the current there, then the voltage current ratio is same if I interchange the source and the shorting terminals, alright. That means the impedance, it is an impedance basically V1 by I2, this is the expression for an impedance, this is an impedance. The voltage applied at this port and the current measured at this port, the ratio is same as when we get the same similar ratio of this voltage and this current. This is known as reciprocity theorem.
The response to excitation is constant.
Response to excitation is constant between two ports. So, in general we will write for an N port this is Vj, this is shorted, this is an emitter, okay. This is IK, this port is shorted, and here we apply a voltage Vk, this current is Ij, Vj by Ik is equal to Vk by Ij, okay. Next we go to the transmission parameters. We write the equations like this: V1 equal to A times V2 minus B times I2, I1 is equal to C times V2 minus D times I2. So, or in matrix form, V1 I1 equal to A, B, C, D, I1 minus, sorry, V2 minus I2. Okay. So, what will be A? V1 by V2 when I2 is 0. Is that all right? That means, once again refer to a T network. This is say ZA, ZB and ZC. What does it give you? What is V2 by V1? You have seen V2 by V1, in this case V2 is under open circuit condition, it is ZC by ZA plus ZC, is it not? A is just inverse of this. Is it not? You can write in terms of Z11, Z12, Z22. How much is ZA plus ZC? If you remember, Z11 and ZC was Z12. If you just refer to the earlier discussions. So, A can be written as Z11 by Z12. Similarly, what will be B? B is minus of V1 by I2. B is minus of V1 by I2. And what is V1 by I2? V1 by I2 when V2 is 0, that is short circuit condition. So, under short circuit condition, what should I write? In terms of Y, that would be better. Let me write in this form. So, V1 by I2, that means I am shorting this. Okay. If I short this, voltage V1 is applied across YC, YB is redundant. So, V1 by I2 is how much? I2 is in the opposite direction. So, minus and minus and minus will make it plus. So, it is just YC. Okay. So, it is 1 by YC. And what is yc in terms of y parameters? Minus of y12, if you remember, is it not? This was the transfer admittance. C, how much is it? I1 by V2 when I2 is equal to 0, that means again open circuit condition, alright. Under open circuit condition, I1 by V2, so when I2 is 0, keep this open, send a current of 1 ampere, how much is V2? ZC, so 1 by ZC. And what is ZC in terms of Z parameters? Z12. You remember, whenever we have open circuit parameters, we will refer to an equivalent star, alright, T connection. Whenever we have short circuit parameters, we will immediately refer to a delta. Then it is easier to link up y11, y12, y22, similarly z11, z12, z22. In terms of these, I can immediately write. Okay. Could someone tell me what will be D? D is again I1 by I2 under I1 by minus I2 when V2 is 0, alright. So, I will refer to the short circuit parameters. So, I short this, and how much is I1? I1 is this current, and this entire current through YC will flow through the short circuited path. So, I2 flows through this. So, it is this current by this current. So, what is this current? What fraction of the main current is this? Yes. Yes. If you talk in terms of impedance, say it is ZA by ZA plus ZC, is it not? So, I1 by I2, I1 is a higher current, so it will be ZA plus ZC by ZC, which means what? Z is 1 by YA, 1 by YB, 1 by YA plus 1 by YC by 1 by YC. So, how much is it? How much does it come to? YA plus YC by YA. And what is YA plus YC? Y11. Will there be a negative sign? So, there will be a negative sign, and Y11 divided by YA. Y11 plus Y12. So, this will be D. Is that all right? So far we have expressed the ABCD parameters in terms of Y or Z parameters. Now, I leave it as an exercise to all of you to, we will take it up in the tutorial class also later on, we will cross check. Write Y and Z in terms of ABCD, rather write any set in terms of any other set. Make a table, Y, Z, and in some books they write matrix A, that means A, B, C, D, okay. Y, Z, A, Y, this is 1, I mean it is identical, this, so this need not be filled up. Z in terms of Y, it will be basically Y matrix inverse. So, whatever is the determinant and then all those you compute and then substitute here. Z in terms of Z, it is same. Z in terms of A, this is what you have to do. A in terms of Y and Z, that we have already seen. Now, I have written A in terms of Z11 and Z12. Can you write totally in terms of Y's? Z11 you can write in terms of Y, Z12 you can write in terms of Y. So, it should be finally converted to all Y's. Similarly, I must have A in terms of all Z's as well as all Y's. Similarly, B also, from here you can also write in terms of Z, because you know the relation between Y and Z. Similarly, C and D. So, you complete both these matrices. What will be A, B, C, D in terms of Y's? What will be A, B, C, D in terms of Z's? Okay. Similarly, Z in terms of A's, B's and so on. What will be the values in terms of A's and B's? So, complete this table. Okay. Now, let us take up one or two simple examples. There is a network, very simple network. First example is a network consisting of an impedance like this. These impedances are not there, they are open. What will be the Z parameters? Z11 equal to Z12, Z22. Now, could you please tell me what will be Z11, Z12 and Z22? Similarly, what will be Y11, Y12 and Y22 for this network? Now, let us see what will be Z11. So, we will be completing this network either in terms of a pi or a t. For Z, it is convenient to go for a T network. So, I will break it up into two halves and then I will put one impedance here whose value is infinity, as if the midpoint has been connected to the ground, to this reference line, by an infinite impedance. Okay. So, this is Z by 2 and infinity. So, how much will be Z11? It will be Z by 2 plus infinity is infinity. What about Z12? This one is also infinity. Z22, Z by 2 plus infinity. So, all the three will be infinity, so far as the Z parameters are concerned. What about Y? Once again, here I can assume this to be a pi network where this admittance is YB is 0, infinite impedance means admittance is 0, YA is 0 and this is YC which is 1 by Z. Okay. So, how much will be Y11? YA plus YC, that is 0 plus 1 by Z. So, this is 1 by Z. Similarly, Y22 will be 0 plus 1 by Z. Okay. And Y12 is minus 1 by Z. All right. This is something very interesting. The Y matrix parameters, the Y parameters are all finite, whereas the Z parameters are all infinite. There is no finite Z matrix, whereas there is a finite Y matrix. What does it mean? It is inverse of this, so inverse does not exist. It is going to give you a singular matrix. Let us see. Y matrix is 1 by Z minus 1 by Z minus 1 by z, 1 by z. What is the determinant? 1 by z square minus 1 by z square 0. So, the determinant is so z does not exist. I hope this is clear. Let us take up another example. Now we have just one shunt element. What would be the z parameters and y parameters? Z11 is how much? So I can once again put a fictitious element here whose impedance is 0. So ZA is 0, ZB is 0 and ZC is 1 by y. So how much is Z11? ZA plus ZC, is it not? That is equal to 1 by y. What about Z22? Similarly 1 by y, okay, and Z12, yes, Z12 will be again, no, Z12 does not have a negative sign, it is Y12. In the short circuit case only you get negative sign, in the impedance terms you do not get any negative sign. So Z12 is just this impedance which is 1 by y. So now the Z matrix is finite, you can imagine its inverse does not exist, because you can see the determinant will be 0, it will be y, 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 1 by y, 1 by y, 1 by y, 1 by y. So that will give you 0. So that can be verified from here. If I draw the equivalent pi, this y I can distribute into y by 2 and y by 2, okay, and in between I put y c equal to 0, 0 admittance, sorry, infinite admittance. There is a short circuit, so infinite admittance. So what will be y parameters then? Y11 is y by 2 plus this one, which is infinity, capital Y by 2 plus infinity, so that is infinity. What about Y22? Similarly again y by 2 plus infinity, so infinity. And what about Y12? Yc, that is minus infinity. Y12 will have a negative sign of the actual admittance. So it is 1 by y, 1 by y, 1 by y, 1 by y. This was our Z matrix. Alright. So inverse of that Y matrix will be Z inverse, okay, that is infinity, 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 okay, because the determinant does not exist. Otherwise also it is verified from here. A third example we will take an L connection ZA and ZB. What will be Z11? Z11 will be ZA plus ZB, Z12 ZB, and Z22 also ZB, because I can always assume a 0 impedance value here. So, this plus this will be ZB itself. Okay. Now, if you are asked to calculate the Y parameters for this, then I will take an equivalent pi. So, this is 1 by ZA admittance, this admittance is 1 by ZB, and what about this admittance? Infinite impedance, that means admittance is 0. Okay. Now, you calculate the Y parameters. What will be Y11? Y11 is this plus this, so 1 by ZA. Okay. Y22 1 by ZA plus 1 by ZB. Thank you. And Y12 minus 1 by ZA. Is that all right? You will find if I take the inverse of this matrix, I will get this ZB. Elements of this Z matrix will be like this. Now, sometimes we are given a network in this form. It is a bridged network, 2-port network which is bridged. This can be conceived as two 2-port networks which are connected in parallel, okay, as if I am having this one, I call it network A plus network B. This is only an example, it can be anything. If I can break up that network into two separate networks like this, which are put in parallel. When I say the two networks are in parallel, what are the common features? What are the things which are common? The voltage applied here, V1 and V2 are same. If I call it V1A and V2A for this network, V1B and V2B, then V1A equal to V1B is equal to V1 and V2A is equal to V2B is equal to V2. This voltage is same as this and this. This voltage is same as this and this. Okay. Therefore, for this network, if we write the equation, say I1A and I1B, then I1A plus I1B will be total I1. Okay. So, V1 I1A I1B I2A can be written as Y11A Y12A Y21A and Y22A into V1A and V2A, okay, which is nothing but V1 and V2. Okay, this is V1 and V2. Similarly, the second network is I1B I2B equal to Y11B Y21B y1 to b, y2 to b, v1b, v2b. Since this vector is same as this vector, so and these elements can be added together to generate the total current vector, this plus this. So I1 I2, which is nothing but this plus this, will be equal to y11a plus y11b. Similarly, y12a plus y12b, and so on. That means element wise you add the values of y parameters, and then this vector is same as this, so I will write straight away v1 and v2. That means the admittance matrices are added together for the two sub networks when they are in parallel. Is it all right? This is quite common. You can have a bridged T network. You can have a bridged T network. So if I ask you, say this is ZA, ZB, ZC. I will call it ZA1, ZB1, ZC1. Okay. Another set ZA2, ZB2 and ZC2. If I am given a network like this, what would be the voltage current relations? This is I1, this is I2. How do I write like that? This can be written as two separate networks, networks 1 and 2, ZAI, ZBI, where I is taking two values, I1 and I equal to 2, ZCI corresponding I1I, I2I. I can write like this. Same voltages V1 and V2. I need not write V1I because voltages are same. V1I, V2I, etc. will be same as V1, V2. Therefore, from here you write the y parameter values. Okay. You have to just go for star to delta transformation, or by the earlier method short circuit, by applying short circuits you can write in terms of these impedances. Once you know in terms of ZAI, ZBI, ZCI, you write and then substitute the values, the exact values for these, for the two cases, and then add them together. So Y matrix will be Y11I summation over I, Y12I summation, Y21I summation. These are identical. Y22I summation. Okay. So this is a twin T network which can be reduced from a star to a delta, and directly you can write these. Star delta conversion you have done. So basically star to delta you have to do, you have to write the admittances. Next, suppose you have two such two port networks in cascade, that is they are put in cascade like this, I1, V1, I2, V2. Again this I2 becomes I3, I4, I2 is minus I3 or I3 is minus I2. Okay. Suppose this is the first set A, B, C, D for network 1, A, B, C, D for network 2. So, I will call it A1, B1, C1, D1, A2, B2, C2, D2. So, V1, I1 is equal to A1, B1, C1, D1 into V2 minus I2. Okay. Then the same V2 is appearing here. So, V2 is equal to V3, V3 I3 equal to A2, B2, C2, D2 into V4 minus I4. Now, what would be the relation between V1 I1 and V4 I4? If V2 is equal to V3 and I2 is minus I3, so can you try that? You will find the ABCD matrices are just multiplied, that will give you the overall ABCD matrix. So, I want V1 I1 in terms of A, B, C, D, V4 minus I4. So, what is this ABCD? Is it the product of these two matrices? You have to establish that, do that. You can see V2 minus I2 is same as V2 is equal to V3, I can write V3 into I3, this is same as this, is it not? Because minus I2 is I3, so you can replace it, so it becomes this into this into this. So, ABCD matrices will be just multiplied. Now, in a practical situation, you have, say in a transmission system, you have a transmission line of some dimension, some height, okay. Then you change the height, there is some change in the line parameters. So, ABCD parameter values also change, and if they are put in cascade, alright, there is no tapping of power as such, but they are put in cascade. Even if there is some tapping, it really does not matter, because that will be giving you some shunt element only. So, overall ABCD parameter will be the product of these two ABCD matrices. So, A will be, overall A will be A1 A2 plus B1 C2. B will be see this multiplied by this A1 A2 plus B1 C2, then this multiplied by this. So, A1 B2 plus B1 D2, A1 B2 plus B1 D2. Mind you, this coefficient, this element A is the ratio of two voltages. So, it is a dimensionless constant. dimensionless parameter. Okay. Now, does, it will have a magnitude. Does it have an angle? It may have an angle. So, if the impedances are complex, normally in a transmission line you have RLC, so impedances are in a complex form. So, the ratio can be a complex constant, dimensionless, but it may have an angle. So, here also we find it is the product of two dimensionless quantities, it is this. B1, what was the dimension of B1? Say B is the ratio between voltage and current, that is impedance, and C is current and voltage, that is admittance. So, B and C product will also be a dimensionless quantity, one is mho, the other is ohm. So, this conforms to the dimension of this. Similarly, B impedance, this one is impedance multiplied by a constant, is also impedance multiplied by constant, because D has the dimension of it does not have any dimension, it is the ratio of two currents. So, similarly C and D you can write. So, we will stop here for today, and next time we will take up we will discuss something about hybrid parameters, and then we will take up some numerical problems. So, the next class will be a tutorial class on whatever we have covered so far. We will have some problems. Okay. Thank you very much.
1951. A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur has blossomed into a time-tested, venerable institute of learning, with the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology, and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems, and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. That ensure a student's mind develops at the right pace. Devoted full-time to handle industrial projects and consultancies and for deploying and propagating intellectual property. Successful sponsored research projects straddle a wide spectrum, ranging from computers, communication and biotechnology to robotics, photonics, and food processing. The setting up of a state-of-the-art VLSI CAD laboratory and tie-ups with GE in areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire.
आदर्शाय मादर्शाय प्राणदास्मह्वयम् योगकर्मसु कौशलम् योगकर्मसु कौशलम् योगकर्मसु कौशलम्.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.